friends, in the last video I have discussed about the three different Einstein coefficients associated with the interaction of radiations with matters. Today we will look into the relation between those Einstein coefficients. In the last video we have seen that when some radiation interacts with matter, there are three different types of processes occurs, right? One is absorption, spontaneous emission and stimulated emission. And there are three rates associated with these three processes. We have derived the equations. The first one is rate of absorption, that is minus dN1 by dt is equals to B12 N1 E nu 12. Here N1 is the population of atoms in the state 1 or ground state. B12 is 1 Einstein coefficient and E is the energy density. Just for convenience, here what I am doing, I am replacing this nu 12 as simply nu. That means nu is nothing but nu 12. So the rate of absorption is equals to B12 N1 E of nu, right? The second one what we have seen is rate of spontaneous emission, that is equals to minus dN2 by dt, and this Sp denotes this is spontaneous emission. What is the expression? We got this is equals to A21 N2. This is the Einstein coefficient of spontaneous emission and N2 is the population in the excited state or state 2, right? Third one was rate of stimulated emission, and that is equals to minus dN2 by dt. St denotes this is stimulated emission. What was the value for this? This is equals to B21 N2 E nu 12, right? Here B21 is Einstein coefficient of stimulated emission, N2 is the population in the excited state or state 2. E nu 12 is the energy density. Here also I am just replacing this nu 12 as simply nu, just for convenience of writing. Okay. Further, we have seen that this B12 is Einstein coefficient of induced absorption, A21 is Einstein coefficient of spontaneous emission, B21 is Einstein coefficient of stimulated emission. And here we have seen that this B12, this is associated with the transition which occurs from state 1 to state 2, and these two are associated with transitions, those are from state 2 to state 1. So this is for absorption and these two are for emission. Further, we have seen that letter A is used when the transition occurs by its own without any external trigger, and letter B is used for transitions which are induced by external photons. Okay. So basically these are the three Einstein coefficients associated with different processes when radiation interacts with matter. Now we will see what is the relation between these three Einstein coefficients. For deriving the relation between these Einstein coefficients, we have considered some assumptions. The first one is that the atoms and radiations are in thermal equilibrium. The second assumption is that the radiations obey Planck's law at any temperature. That means these are identical with black body radiations. And I have already discussed about this Planck's law under quantum mechanics. You can go and check there how to derive the expressions for energy density using Planck's law. I shall give the link in the description box. The third assumption is that the population densities N1 and N2 are given according to Boltzmann distribution law and are constant in time. So these are the three assumptions we are considering to derive the relations between Einstein coefficients. The first assumption what we have considered is that the atoms and radiations, they are at thermal equilibrium. So at thermal equilibrium, what happens? The rate of absorption should be equals to rate of total emission. We had three different processes, right? One is absorption, in which case the atom is moving from ground state to excited state. And emissions, we are having two types of emission. One is spontaneous emission and the second one is stimulated emission. So the total rate of absorption should be equals to the total rate of emission. So I can write rate of absorption is equals to sum of rate of spontaneous emission and rate of stimulated emission. Because there are two types of emissions, we have to take their sum. Okay, and we have already obtained the expressions for these three rates. So rate of absorption is equals to B12N1 E nu. Similarly, rate of spontaneous emission is equals to A21 N2 and rate of stimulated emission is equals to B21 N2 E nu. Now in this term and this term we are having this expression E nu. So I can take this to the left hand side. Then what I can write? B12N1 E nu. If I am taking this to left side, this will be minus. Okay. So minus B21N2 E nu is equals to A21N2. Now from these two terms, I can take this E nu common. So after taking that E nu common, I can write E nu B12N1 minus, here it will be B21N2, and that is equals to A21N2. Now from here I can write this E nu is equals to this, I have to take to the right hand side, right? So E nu is equals to A21N2 and this term, this will go to the denominator. So it is B12N1 minus B21N2, right? So the expression what we obtain is equals to E nu, that is the energy density, is equals to A21N2 divided by B12N1 minus B21N2. Now dividing both numerator and denominator with B12N2. So I am dividing here B12N2, here also B12N2 and this term also B12N2. So here this N2 and N2 will get cancelled. Here B12 will get cancelled. Again here this N2 and N2 will get cancelled. So what is remaining? E nu is equals to, here I am having A21 divided by B12. So A21 by B12. Similarly here N1 by N2 minus B21 by B12. So this is the expression. Now we will be considering the third assumptions. What is the third assumption? The population, they obey Boltzmann's statistics. So according to Boltzmann's statistics, N1 by N2 is equals to e to the power minus E1 minus E2 by KT, because that is the number is directly proportional to or is equals to e to the power minus E by KT. Okay, so N1 I can write this as minus E1 by KT, N2 I can write minus E2 by KT. Then if I am taking that to the up, that will becomes plus E2 by KT, and taking minus sign common, I can write it as E1 minus E2 by KT. Okay, so this is the Boltzmann statistics. Now from here we know that E2 minus E1 is equals to h nu. Okay, so E1 minus E2 will be minus h nu. So minus h nu, that will become plus h nu. So here I can write N1 by N2 is equals to e to the power h nu by KT. Okay. Now substituting this value over here, I can write E nu is equals to this A21 by B12, this is here, 1 by, in place of N1 by N2, I am writing e to the power h nu by kt minus B21 by B12. So finally what we obtain? E nu is equals to A21 by B12, 1 divided by e to the power h nu by kt minus B21 by B12. Now we will use the second assumption. In the second assumptions, what we have considered, the atoms, they are obeying or they are according to Planck's distribution or Planck's law. Okay. So according to Planck's law, the energy density is given as 8 pi h nu q by cq into 1 by e to the power h nu by kt minus 1. This derivation we have done under the first unit, that is quantum mechanics. I shall give the link for this derivation in the description box. If you want, you can go and watch that video. Okay. So this is the energy density derived by Planck's. Now as we have assumed that here the atoms, they also obey the Planck's law, then now comparing these two expressions, I can write here, if you will compare, here it is A21 by B12 and here we are having 8 pi h nu q by cq. Similarly this one is same, but here I am having B21 by B12, here I am having 1. So comparing these two, I can write B21 by B12, that should be equals to 1. So from here what I can write, B21 is equals to B12 just by taking here. Okay. And the other thing is what I can write, A21 by B12, that should be equals to this value, that is 8 pi h nu q by cq. These two are known as Einstein relations because we are having three Einstein coefficients. One is A21, one is B12 and the third one is B21. So these two relations, they are relating the three Einstein coefficients and hence it is known as Einstein relations. Let me just do some modifications over here. This is B21 is equals to B12. And from here I can write B12 is equals to this CQ will go here and this 8 pi h nu q, it will come down. Okay. So combining that I can write B21 is equals to B12, that is equals to this CQ will go up, so it is CQ divided by this will come down 8 pi h nu q and A21 was there. Okay. So this is the relation between all the three Einstein coefficients. Okay. Now let us see what are the conclusions we can draw from these relations. So these are the two relations. First I am considering this first one. Okay, that is B21 is equals to B12. Here what is B21? This is nothing but the Einstein coefficient of stimulated emission, and B12, this is nothing but Einstein coefficient of absorption. So from here it is clear that the Einstein coefficient of absorption is numerically equal to the Einstein coefficient of stimulated emission, and these two are related to the rate of absorption and stimulated emission. So from here I can also write that when a radiation field is applied, the probability of upward transition, that is absorption, is equal to the probability of downward transition, that is stimulated emission. Now coming to the second expression, this is the second relation. Okay, this one was between coefficient of absorption, this is coefficient of absorption, and coefficient of stimulated emission. Now this one, if you will see, A21, this is coefficient of spontaneous emission, and this one is coefficient of stimulated emission. So this second relation, this gives us the relation between the coefficients of spontaneous emission and coefficient of stimulated emission. And from here, if you can see, this ratio is directly proportional to nu q, because this rest of the terms over here, they are constants. 8 is constant, pi is constant, h is Planck's constant, that is also constant, c is velocity of light. So all these terms over here, these are constants. That means this ratio is directly proportional to cube of the frequency of incident radiation, right? So the ratio between coefficient of spontaneous emission and stimulated emission is directly proportional to cube of the incident frequency. Now from here, if I increase the value of this incident frequency, then the probability that, because this ratio will be more, that means this probability of spontaneous emission will be more as compared to probability of stimulated emission, right? So at high frequency, the spontaneous emission is more probable than stimulated emission. But if you recall, the condition for laser is that the stimulated emission should dominate absorption and spontaneous emission, right? So if at high frequency the spontaneous emission is more probable, then to get lasing action at high frequency is less, right? So that it is difficult to achieve laser action at high frequency as compared to lower frequency. At higher frequency, the spontaneous emission will dominate, okay? But for lasing action, we need that the stimulated emission should dominate, and for that the frequency should be low. So these are the relations between the Einstein coefficients. Now we have already know that the stimulated emission should dominate spontaneous emission and absorption to have this lasing action, right? So how can we get that condition? What are the conditions for this lasing action? What are the requirements so that the stimulated emission will dominate over absorption and spontaneous emission? That we will discuss in the next class. Today we will stop here. Thank you all for your listening. If you like the content of the video, please press the like button and share the video with your friends. Also do subscribe to my channel to get the notifications whenever I am uploading a new video. Thank you all.